Welcome to part 2 of the stoichiometry chapter. This section is probably the most important one of the whole chapter because it gets into calculations using the mole map. For this section, we're going to use the mole ratios that we learned in the last section, plus we're going to make a new and improved mole map, similar to one that you saw 2 chapters ago, but even better. To think about what goes into our calculations, think about what kind of units we could convert into moles when we did the mole unit before. Hopefully you remember that we were able to convert mass, that is measuring the grams of a substance, into moles by using molar mass. We were also able to convert pressure, volume, and temperature of a gas into moles by using the ideal gas law, PV equals nRT. And finally, we were able to convert particles into moles. Remember, particles included molecules, atoms, and ions. All of those units were things that we could convert into moles. Well, as we saw in the last section, we can convert between moles of 2 different substances. In order to do this, we're going to make a new and improved mole map. In order to convert between any types of substances, we should be able to convert any unit of reactant or product to any other unit of reactant or product by using the mole ratio. And where we get the mole ratio from is the balanced chemical equation. Remember, specifically, it was the coefficients in the balanced chemical equation where we found our numbers to use in our mole ratios. What we're going to do next is going to look a little scary at first, but we're going to make a giant improved mole map. On your paper, you see a large blank space for this. In this large blank space, I'm going to have you start by filling in the left-hand side of this mole map, then we'll fill in the right-hand side. So let's take a look at the left-hand part of the mole map. Okay, here's the left-hand side of the mole map. It looks kind of scary to start with, but I would recommend that you pause this video and copy down what you see for this half of the mole map. Okay, now that you have this written down on your paper, let's take a minute and talk through. So hopefully you're done writing and you can just follow along and listen and look at what I'm pointing out here. Notice that in the center of this map, we have the mole. Before we just said moles in general. Now I'm being more specific and I'm saying moles of A. A represents a substance, a chemical. The reason I'm designating it A is because I'm going to get 2 substances involved here. So I'm starting with a chemical A. I could convert that substance A between moles in the center of my mole map and particles or molecules, which is the most common type of particle. If you remember, if you look on your old mole map, you see that the conversion for that was that 1 mole of your substance was equal to 6.022 times 10 to the 23rd particles or molecules. This was Avogadro's number, and remember it was used for counting, and that was our way of converting between particles and moles. So that's one leg of the mole map. Another leg of the mole map that you should recognize is the calculation of mass, or grams. To calculate the grams of a substance A, we used the molar mass. Molar mass, remember, was a value that we got from the periodic table. That's what my PT here represents, periodic table. We added up the masses from the periodic table, and that told us how many grams of a substance was equal to 1 mole. Notice that in both of those conversions, the mole did indeed have a 1 in front of it. This is always true when you're converting for one substance at a time. It's how many particles or how many grams are equal to 1 mole of a substance. The third and final leg that you recognized from before had to do with gases. If you're talking about a gas and you know the pressure, the volume, and the temperature, we could use the ideal gas law, which I squeezed on this arrow here. It says PV equals nRT. In the equation PV equals nRT, remember that N, the lowercase n, represented moles. So if we knew P and V and T, R was a constant, we were able to find the value for number of moles. N. So that was a third way we could convert between moles and a different substance. Now you'll notice all of those were moles, grams, particles, and PV and T of A. The new part of the mole map is what we have learned to do this chapter with moles of a substance. We learned in part 1 how to convert between moles of a chemical A and moles of a different chemical. Let's call it chemical B. So the A and the B represent two different chemicals. To get between moles of two different chemicals, so between moles of A and moles of B, we did that by making a mole ratio. So a mole ratio is what I have on the arrow here. And to make a mole ratio, I used the coefficients from a balanced chemical equation. What I'm going to do now is remove the rest of this screen shield and let you write down the whole rest of the map. So go ahead and pause it and copy down the rest of the map. As you look at the right side of this map, hopefully you notice some symmetry. Everything that we had on the left is also apparent on the right. For example, we had moles of A on the left, moles of B on the right. We got between them with a mole ratio. We had grams of A at the top left, and here I have grams of B in the top right. Again, to convert between moles and grams, you would use a molar mass. This time, though, you would use the molar mass of your substance B. That molar mass from the periodic table would be equal to 1 mole of the chemical B. Likewise, we can use PV equals nRT, the ideal gas law, to figure out the pressure, volume, and temperature of our gas B. And we can use Avogadro's number, 6.022 times 10 to the 23rd, to convert between moles of B and molecules of B. So what you have here is very symmetrical, although mine isn't written very neatly, I apologize for that, but you have a symmetrical mole map here. Notice that the mole does indeed have a coefficient of 1 in front of it in every place except for one place. The only time we don't use ones in front of the mole is when we make our mole ratio. The mole ratio is where we use coefficients to convert between moles of two different substances. Now what I'm going to do with this mole map, which looks really scary, is I'm going to try to use it in a problem. We'll do one together, and then you can try a couple on your own. If you look carefully at this map, you should find that all of the arrows are going from left to right. This is intentional because this map is made to be read from left to right. For example, you would determine in a problem whether you're given grams, pressure, volume, and temperature, molecules, or moles of a substance A. You can look on the map to determine which box you're starting in, and then you follow the map to turn it into whichever units I ask you to find of your chemical B. For example, moles, mass, pressure, volume, and temperature, or molecules or particles. So this is really a guide to help direct your calculations. This is probably the most important piece of information in your whole notes packet, so you'll probably be flipping back to this page a lot because as you do your calculations, this is your map, this is your tool to get you from point A to point B. Let's go ahead and try a problem. All right, let's look at practice problem 3. It says, if you add water to calcium carbide, which is CaC2, you will produce acetylene gas, C2H2. Acetylene gas is used as the fuel in torches, like for welding and things like that. So that's why I have a picture of a torch burning over here. If you have 125 grams of calcium carbide, CaC2, how many grams of water do you need to react with it? So let's check out where we are in this problem. We are given 125 grams of CaC2. Grams would be a mass. CaC2 would be my chemical A, the chemical that I'm given a value of to start with. Then let's look what they're asking me to find. They're asking me to find how many grams of water. Grams is also a measure of mass, but notice that water is a different chemical than the calcium carbide I started with. So water would be my chemical B. So What we're trying to do here is we're trying to get between a mass of A and change it into a mass of B. If we look on our mole map, what that means is I'm starting at mass of A, and I'm going to convert it to moles of A, then to moles of B, and finally up to grams of B. So this map can be helpful to direct your calculations. Let's focus on the first step first. I'm going to start with the grams of A, and I'm going to change it to moles of A. In order to do this, I need to use the molar mass of A. So for this problem, I'll start by writing down the number I'm given, which is 125 grams of CaC2, calcium carbide. Times in a line, or make your bridge or your table. The unit you start with has to go in the denominator, so grams of CaC2 goes down here. Moles of CaC2 goes in the numerator. Let's flip back to our mole map to check out the numbers. I see here that for this step, it's always 1 mole of my chemical A is equal to the molar mass for the grams. So in this particular calculation, I have 1 mole of CaC2, and I need to fill in the molar mass of calcium carbide down here. Somewhere off to the side on my paper, I will calculate that molar mass. The mass of 1 calcium is 40.08, plus the mass of 2 carbons would be 2 times 12.01. When I add that up, I find a molar mass of 64.10 grams per mole. So that 64.10 goes for the molar mass of calcium carbide. As far as units go, my grams of calcium carbide cancel, and right now I'm at moles of calcium carbide. Now I'm ready for another step. Let's take a minute and look at our mole map to see where we're at. In my first step, I got to moles of A, moles of calcium carbide. For my next step, I need to make a mole ratio and change that into moles of the chemical B. My chemical B here is water. In order to make a mole ratio, I'm going to look at the coefficients from my balanced chemical equation. So right here, I had moles of CaC2 in the numerator. So in my next step, the moles of CaC2 needs to go in the denominator. A mole ratio means I'm changing from moles of one chemical, the CaC2, into moles of another chemical. Here, it's the water. So I would have moles of H2O on top because the water is the chemical they asked me to find. In order to fill in this mole ratio, I need to look at the coefficients of the chemicals. Right here, calcium carbide has no number in front of it, which is an understood 1. The water has a 2 in front of it. That 2 would go in front of the moles of H2O right here. At this point, my moles of calcium carbide would cancel out. Right now, I'm at moles of water. So on my mole map, I'm currently at the moles of B box, and I'm trying to find a grams, a mass of B. So to do that, I need to go up this arrow by using the molar mass of B in order to find the grams of B. Now I need to be careful because this is a different chemical. This is B than the one I had before, so it has a different molar mass. Right here, I'm going to put another times in a line. I had moles of water on the top, so I'm going to put moles of water on the bottom. And I'm trying to convert moles back into grams, or mass. So I would have grams of H2O in the numerator. For this conversion, the moles of water gets a 1. This is always true when you're doing a molar mass, that you use 1 for the moles. What I need on top is I need the molar mass of water. So to find the molar mass of water, I would add up 2 hydrogens plus 1 oxygen to get a total molar mass of 18.02. That molar mass is going to go right up there in the numerator, in front of the grams of water. If you're wondering why I didn't get 18.016, the answer is I did, but I had to round it. Because this molar mass only went to 2 decimal places. When you add with significant figures, you can go to the least decimal place that they all have in common. This one went to 3, this one went to 2. The least thing that they have in common is 2, so my answer only goes to 2. Finally, I can cancel out some units, moles of water, and now I'm ready to actually type this in my calculator. There are a couple ways you can enter this in your calculator. One is to multiply everything on the top, write it down, multiply everything on the bottom, write it down, and then divide. I prefer to do it one step at a time. For example, I started with 125. In the next step, I would multiply by 1. Of course, when I multiply by 1, it doesn't change the value. And then I would divide by the number in the denominator, 64.10. If I were doing this on my calculator, I would keep going. I would multiply by 2 because it's on the top, and then I would divide by 1. Then in the next step, I would multiply by 18.02 and divide by 1. Now, of course, what you find when you do this is that all these things where I multiplied by 1 and divided by 1 don't actually change my answer, so I don't really need to type them. When I typed this in my calculator, I got a long answer of 70.2808 blah blah blah. To write my answer with the correct number of significant figures, I'm going to look at what I started with. I started with 125, which had 3 significant figures. My answer should have 3 significant figures. Now, since there's an 8 after this 2, that means it's going to have to round up. So I get 70.3. Now, the label on this is grams of water. Those are the only units that didn't cancel out in my calculation, and there is my answer. Next on your paper, you see practice problem 4. This video will end. You should go look at your mole map, try to solve practice problem 4 on your own, and then watch the file that has the solution to practice problem 4. Good luck. Use your mole map.